So to look at the distortion and then to quantify it, let's start with linear loads first. So just a single phase circuit here, we have this linear load connected to it. Voltage is given by this phasor. This current here is given by this phasor right here at some power factor angle phi. The power that is being supplied to this load here is voltage times the current times the power factor cosine phi, and which is real power supply divided by the apparent power, which is the product of voltage and current. And rewriting this equation, we can see that, if I may erase this ink here, that the current can be written like this here. So for a given power, higher the power factor, lower would be this current. So as power factor goes higher, the amplitude of the current, the magnitude of this current decreases. So the RMS loss on the utility system would be smaller, because that's I squared R, right? So if I is small, I squared R is the power loss, that will be small. So utilities would prefer that this power factor ideally is equal to 1. That is, phi is equal to 0, the angle between the voltage and current, okay? All right, but when it comes to distorted current, which will be drawn in this power electronic based load, for example, if you had this diode front end, and if you terminated this with a large capacitor, and then you have another converter, but just looking at this utility side converter here, the current drawn here, if it's a single phase input, it may look something like this, as shown by this I sub s, okay? And as you can see by this solid curve, for I sub s, it's not sinusoidal, but of course it's repetitive, and therefore we can do Fourier analysis and find the fundamental frequency component, let's say IS1. So we define the distortion in this current as the actual current that's drawn, which is IS, minus its fundamental frequency component, IS1. So this distortion current, as you can see here, is plotted in this figure right here, okay? And also you can see here that this the angle at which this fundamental frequency component is crossing is drawn here as well. All right. So to analyze this distorted current waveform, which is repetitive, we can apply Fourier analysis. But we are not going to go into that. And the best way to analyze these is to go to a simulation program like PSpice or EMTDC, and you can analyze these things in these computer programs. And just as an example, if the current that is drawn looks like this square pulse over here, the fundamental frequency component IS1 is shown here, and the difference of these two, I distortion, is shown over here, just as an example. All right. So coming back to this distorted current, we saw that this current is distorted. It's flowing just for part of the cycle, during the positive half cycle like this, negative half cycle like this. It's distorted, but the question is, how distorted is it? We really should quantify it, okay? And to quantify it, we have, people have agreed on this index here called total harmonic distortion, in short THD. And that is defined as the RMS value of this distortion current, which is this RMS value, divided by the RMS value of the fundamental frequency component, IS1 here. Okay, so that's is called the total harmonic distortion. And then the displacement power factor, which is not the same as power factor, this dPF is cosine of this angle phi1. Phi1 is the angle at which the fundamental frequency component is crossing the 0 axis. Okay. So because the distortion component is made up of different frequencies other than the fundamental, we can come up with the RMS value of this component IS, not component, of the total current IS. So we can come up with the RMS value by looking at the square of the fundamental frequency component and the square of the entire distortion component RMS value, and then taking the square root of that. So this is can be shown to be mathematically correct. Okay, and then the real power that is transferred by this voltage and current would be only on the by the fundamental frequency component. So the real power is the RMS value of the voltage, which is assumed to be sinusoidal, and then the fundamental frequency of the current times the so-called displacement power factor, okay, which is a cosine of phi1. Okay. So from here, we can see that the power factor, which is still power factor is still the real power divided by Vs times Is. Okay, and remember it's not Is1, it's Is. So the power factor then is equal to displacement power factor times this ratio here, Is1 to Is. Okay, and using these equations, it can be shown to be equal to displacement power factor divided by this factor over here. So when THD is 0, we have sinusoidal currents, and at that time power factor is equal to displacement power factor, and that should be quite obvious. But this displacement power factor and power factor can be quite different based on THD levels. So using the equation derived earlier, THD is plotted on this axis, percentage THD, and the ratio of power factor to displacement power factor is plotted here. So as you can see here, when the THD, the distortion is 0, power factor and displacement power factor, they are the same. But when THD is equal to 100%, power factor is only 0.7 times the displacement power factor. Okay, so displacement power factor may turn out to be very high, close to unity, but that doesn't mean anything, because the power factor may be very poor if the current waveform is highly distorted. Okay, so as a consequence, IEEE has come up with these guidelines, and these have become de facto standards. And it's telling us that this total harmonic distortion in current should be less than 5%, and there are some restrictions on individual harmonic components which are listed here in these columns over here. But if the short circuit ratio, short circuit current to the fundamental current drawn by this load is less than 20, then the total harmonic distortion in the current drawn by this load should be less than 5%. So that's what this row here is telling us here. Okay, and so short circuit current in a system in the supply really depends upon how stiff the system is. So when we plug into the wall, we have a voltage source, but that's not an ideal voltage source. There is some internal impedance Z sub S. So the short circuit current, hypothetically, we wouldn't want to put actual short over here, but this current ISC short circuit is really this voltage that's coming in divided by the impedance seen into this load over here. Okay, Z sub S over here. So a low value of this short circuit current implies that system is not that strong. And if the system is not all that strong, such that the ratio of ISC to I1 is less than 20, then the total harmonic distortion in this current should be less than 5%. But if the system is very strong, then the amount of current, amount of distortion that this current can have could be larger. But by and large, I think not knowing what this ratio really is, many utilities would put out a spec saying that if they're going to buy any equipment, the total harmonic distortion should be less than 5%. All right. So having looked at the power quality issues, the other thing we should be slightly aware of is the need for load management. We saw how this load duration, not the load duration curve, but load curve looks like, time of day, it is like this, and then it peaks. So to avoid this peak over here, what one can do is have different rates at different times of the day. So that's called time of day rate. So if you're doing your laundry, for example, at night, it'll be much cheaper than doing it during the peak load hours. Okay, and that way we can shift some of the load from one time to the other. So some utilities have done things like this. The other is demand side management, where we allow utilities to turn off certain equipment like air conditioners in our homes if that need arises. Okay, and the benefit to the consumer is that they get lower electricity rates by allowing utilities to manage the load in their homes, for example. And large customers can negotiate these rates, and not only for energy, but also for peak load. Those are called demand charges. Okay, so the upshot here is that this load management would become a very important topic as we go forward. And just a slide here to show what the retail price of electricity is in the U.S. And this was taken from this reference here. Okay, and of course these prices are going up very significantly. So we have come to the end of this module, and as a summary, we have looked at distribution systems, we have looked at power system loads, in particular power electronics based loads which are growing, and power quality considerations associated with these power electronics based loads, which can cause the currents to be distorted, but they can also, by having switch mode converters, make sure that the currents drawn from the utility are sinusoidal and at desired power factor. We looked at load management and also price of electricity. So thank you very much.